On page 4, we're going to use the same vectors that we had on the previous slide. We remember that vector u was equivalent to the vector 3, 2 in component or rectangular form, and vector v was the vector -2, -5 in component form. We'd also calculated them in polar form and in the common form, but we'll use these forms of the vectors right now. So I want to find 3u, which means I want to make the vector be 3 times longer, and I want it to go in standard position. So you can see that I graphed actually vector u right here, and then I graphed vector 3u, that is 3 times longer, traveling in the same direction. Algebraically, again, it looks like I'm just distributing through to get the vector 9, 6, but if you determine what the magnitude of this vector is with Pythagorean theorem, and determine the magnitude of vector 9, 6 in rectangular form and use Pythagorean theorem, you will find that their directions are the same, but the magnitude of this vector 9, 6 is 3 times bigger than the vector 3, 2. Now on the other hand, if I asked you to find -2v, or -2 times vector v, and ask you to draw it in standard position, I have vector v drawn, left 2, down 5, and I know my vector will have to be 2 times longer, but the negative will denote that it's going in the opposite direction. So algebraically, again, it looks like I just distribute it through. And that is how simple it is if your vector is in the component form or the rectangular form. So the vector 4, 10 with the pointy parentheses is twice as long as v and in the opposite direction. Now, sometimes we have to change vectors from one form to another. I might give you one in one form and you need it in a different form. Or maybe the computations to do some type of combination of two vectors is easier in one form than another. So we need to be able to do this change. And so we want to start with a vector that I'm telling you this is a common form vector. And so be careful. Think common form is the bearing type of angle. So if I have 12 miles and 120 degrees and I want to transform this vector into rectangular form, the first thing you want to do is draw a picture. And so I did that. I know that the length of my vector has to be 12 miles, and my angle, because it's a common form vector, is referenced from north. So I put it in standard position. That's the easiest way to work with this. And so I drew my angle in standard position. And I put my vector with the head here, with the tail here, and the head ends up being in the fourth quadrant because I have to rotate 30 degrees beyond this 90-degree angle. So there's a bearing of 120 degrees, 30 degrees beyond the 90. Now, in order to convert this into rectangular form, first of all, be smart. Look at your numbers. This should have a positive x, and it should have a negative y. So I drew a little right triangle. That's going to help me as a reference triangle to determine my measures. And I'm not terribly concerned when I find this little a and b. I know that this component will be negative and this component will be positive. And I'm not real concerned when I actually do the calculations of them. It will be in the final response that I'll put down. If I need this to be negative, I'll plop a negative sign in front of it. So I can see that this little reference angle here of my little right triangle in the fourth quadrant is going to end up having a 30-degree reference angle. And opposite over hypotenuse is the sine function. So I know utilizing sine, I can determine how long this is. Now again, because it's in the fourth quadrant, when I put it in rectangular form, I will add the negative here. And then my x component for 30 degrees, I know that this is adjacent over hypotenuse, and I can use my basic SOHCAHTOA ideas, and I can determine that that a factor is 10.4 miles. So this would be a rectangular form vector equivalent to this common form vector. And remember, rectangular form and component form mean the same thing. Now, if I want to change a polar form vector to a rectangular form vector, it's basically the same idea. The only thing is when I start with my vector, this angle, because I know I'm in polar form, this is a standard position angle. That means you're starting at the positive x-axis and rotating counterclockwise, as opposed to up here, if it was a common form vector, it was always going from north, going clockwise. So polar form is your traditional way of showing the measure of the angle. So I know I have to rotate 130 degrees from the positive x-axis, and I need to make the magnitude or length of this vector be 30 miles per hour. So this would be an example of a velocity vector. I know its speed and I know its direction. Now I have to determine its component form or rectangular form. So I draw a little picture again, drop the perpendicular down, and I need to find these two little components. Now I know that the A component will end up being negative and the B component will end up being positive, but I'm not worried about that when I actually do the calculations. So 130 degrees, so this little reference angle is 50 degrees. And opposite over hypotenuse, I can use my sine function to determine B. And adjacent over hypotenuse, the cosine of that angle will help me determine what this little a is. When I plot them in the form, I make sure I'm aware that I need to have a negative on this and have this one be positive.